Hello everyone. In this video, we will discuss about the force convection in detail and the overall heat transfer coefficient. We know that the convection is one of the mechanism of heat transfer process. Convection means the heat transfer is achieved by the actual mixing of warmer portion with the cooler portion within the same material. Means it is a bulk movement, right? In the force convection, see basically there are the two types of the convection. One is a natural convection and another one is a forced convection. So forced convection is it is a heat transfer process in which the mixing of fluid may be obtained by the use of stirrer or agitator or pumping the fluid for recirculation purpose. In simply, the convection is done by the external devices known as the forced convection. External devices is it may be either stirrer or agitator or pump. By using these devices, the convection is be done, called it as the force convection. Let us consider the case of heat flowing from the hot fluid through the metal wall into cold fluid. Consider the metal wall adjacent to this hot fluid and cold fluid, and heat must pass through this metal wall to the cold fluid side. The variation of this temperature will be noted here at specific point. See, this is a diagram. It is the dotted line HH and CC, which represents the boundary of the film in viscous flow on the hot and cold side. HH and CC, these are the boundaries in a viscous flow. Viscous flow means the fluid has the zero velocity, but it means the layer of fluid adjacent to this wall it acts as a stagnant film. Stagnant film may produce over here. Okay, the gradient through the line TC and TD caused by the flow of heat whose conductivity is known. Okay, the gradient through the line TC and TD, here is the middle part. The TC and TD means here the actual temperature difference between this metal wall TC and TD, which is caused by the flow of heat whose conductivity is known. Okay, the metal wall thickness is L, which is denoted as the capital L. The hot fluid side, to the right of this HH is a boundary line of this hot fluid side. To this right, the fluid is in turbulent flow on the hot side. Fluid is in turbulent flow means the fluid has the specific velocity to flow. Then TA is the maximum temperature in hot fluid. Here is the TA it has the maximum temperature. Another one, the TB is a temperature at boundary on hot side. Here is a TB, temperature at boundary on the hot fluid side. Similarly, the TC is the temperature at actual interface. Here is a TC, the temperature at actual interface of this metal wall. Now the curve TA, TB and TC represent the temperature difference from bulk of the hot fluid to the metal wall. Here is the TA, TB and TC. This curve represents the temperature difference from bulk of the hot fluid to metal wall. Now this similar concept applied to the cold fluid side. See, to the left of the CC is a dotted line, boundary line of this cold fluid. The fluid is in turbulent flow. Okay, the TF is a minimum temperature of the cold fluid. Here is a TF is a minimum temperature of the cold fluid. Why minimum temperature? Because once the temperature or heat is passes from this metal wall towards the cold fluid, the temperature will goes on decreasing, and TF is the last part of this temperature point. So therefore is it has the minimum temperature of this cold fluid. T is a temperature at the boundary on the cold side. Here is a TE. TD is the temperature at actual interface. The point of TD is here. The temperature at the the actual interface. Now curve TD, TE and TF is represents the temperature gradient from metal wall to the bulk of the cold fluid. The curve TD, TE and TF. This curve represents the temperature gradient from metal wall to the bulk of the cold fluid. This is the overall explanation of this diagram. Now let us consider the surface or film coefficient. The definition of this, it is denoted as H. Okay, the definition is it's a quantity of heat flowing through the unit area of the stagnant film per unit drop in temperature. It's a quantity of heat or amount of heat is flowing through unit area of the stagnant film. Means the heat must passes through the stagnant film, but in unit area. Okay, per unit drop in temperature is per unit difference in temperature. Okay, that means it is the surface or film coefficient, and this is a conductive capacity of the stagnant film for the transfer of heat. Conductive capacity of the stagnant film, this is a surface or film coefficient. Now let us consider the amount of heat is a Q is flowing from the hot fluid side to cold fluid side. At that condition, the same heat must passes through the stagnant film of the hot fluid side, through the metal wall and through the stagnant film on the cold fluid side. See, for better understanding, uh, at both side means hot fluid side and cold fluid side, at the junction of this metal wall means HH and CC, it has the stagnant film, means the stagnant film is formed. Why? Because there is a viscous flow is there, viscous fluid is there. Viscous fluid means there is a zero velocity of this fluid. At that condition, the stagnant film may produce over here. And whatever the heat transfer, we know that the heat transfer is always flowing from the higher temperature to lower temperature one. So therefore, the amount of heat, that is Q, is flowing from the hot fluid to cold fluid, and same heat is must passes through the stagnant film, either from hot fluid side through this metal wall and again through this stagnant film on cold fluid side. Now let the area of metal wall on the hot side is the A1, area of metal wall on the cold side, that is A2, and average area of metal wall, that is AM. Now we consider the surface or film coefficient on hot fluid side. This is denoted as H1 here, 1 for the hot side. Okay, as per definition, the surface or film coefficient on hot side is equal to amount of heat flowing divided by area into temperature in difference in temperature. This is the definition of the surface or film coefficient. But we consider here the hot fluid side only. Okay, that's why here is the H1. So equation is H1 is equal to Q divided by A1 into T1 minus Tc. T1 minus Tc is a temperature drop at hot fluid side. Here we can see here the temperature drop T1 minus Tc at hot fluid side. Okay, this is equation number 1, and this equation and our Fourier equation, it can be seen that the surface coefficient H1 is analogous to the term K by L for metal wall. How? We know that the Fourier equation is Q is equal to Kma delta T upon L. We have to just only substitute this value of this Q in our above equation number 1. H1 is equal to H1 is equal to Kma delta T divided by L into A1 T1 minus Tc after the substitution of this value Q. Okay, because these are the similar or analogous term to this K by L, right? If you revert this equation, means simply the 1 upon H1, then equation becomes 1 upon Kma delta T divided by L into A1 T1 minus Tc. Okay, again we simplify this equation, just only revert this equation again, means the denominator part, that means the L into A1 into T1 minus Tc, just shifted towards numerator side as mathematical rules. Okay, now equation becomes again L into A1 into T1 minus Tc divided by Km into A into delta T. In this, T1 minus Tc and the delta T, these are the temperature drop or temperature difference. So that's why these terms get cancelled. The only remaining part, L divided by Km into A1 is there. A1 and A, these are the area, but area is constant for all. So consider for the only hot fluid side area A1. So therefore L divided by Km into A1. Since L by K is a resistance term for metal wall, we know that resistance term for metal wall, that is L by K. But here the 1 upon H1 into A1 is known as thermal resistance on hot fluid side. Here 1 upon H1 into A1, you can say the thermal resistance for hot fluid side. Similarly, surface or film coefficient on cold side, as per definition, the amount of heat flowing divided by area into difference in temperature. So H2 is equal to H2 for the cold fluid side. Okay, H2 is equal to Q divided by A2 into TD minus T2, means it is a difference in temperature. See in this diagram, the TD minus T2, this is a temperature drop in cold fluid side, and 1 upon H2 into A2, this is a thermal resistance on cold side. And just like a hot fluid side, the thermal resistance on cold side is 1 upon H2 into A2. Okay, for the determination of the overall heat transfer coefficient, we get the three resistance term, say in a series. Firstly, 1 upon H1 into A1 is the resistance on the hot fluid side. Then L divided by K into Am is the resistance of the metal wall, and 1 upon H2 into A2 is the resistance for cold fluid side. Now the overall heat transfer is written as the Q is equal to delta T divided by these three resistance, means firstly resistance for the hot fluid side plus resistance for the metal wall plus resistance for the cold fluid side. Okay, this is a Q is equal to delta T divided by these three resistance. This is equation number 2. If both numerator and denominator of the right side of this equation are multiplied by this A1, means numerator as well as the denominator multiplied by this A1, then we will get the equation, the Q is equal to A1 into delta T divided by 1 upon H1 plus L into A1 divided by Km plus A1 into H2 into A2. Okay, just simply multiplied by this A1. In this first resistance of this metal wall, first resistance of this hot fluid side in 1 upon H1 A1, in that A1 get cancelled. So therefore in equation number 3, denominator side the 1 upon H1 is there only, right? Because here the multiplication of this A1 by both numerator as well as the denominator. This is equation number 3. But overall heat transfer coefficient means U1 is defined as the 1 divided by denominator of this above equation. Above equation means equation number 3. What is the statement or what is the definition of this overall heat transfer coefficient? The overall heat transfer coefficient is just only the 1 divided by the denominator of this equation number 3. Okay, so U1 is equal to 1 upon H1, 1 upon H1 plus L1 LA1 divided by the Km plus A1 divided by H2 into A2. So therefore instead of this value we can put U1 in this equation. Okay, so our final equation is what? The Q is equal to U1 into A1 into delta T. This is a rate of heat transfer equation for force convection. So Q is the rate of heat transfer, that is equal to U1 means the overall heat transfer coefficient into area of heat transfer heating surface into delta T is a temperature drop. This is the overall heat transfer coefficient for the force convection. I hope you understand this video. Thank you for watching.